So in this video, we're going to talk about hydrohalogenation, which is a portion of the reactions of alkenes. So if I take an alkene, in this case, if I take an alkene and I add HX, where HX can be HCl or HBr or even HI, etc., right? If I take the HX addition, what I get is I lose a double bond, right? So I add H, but I also add X, and I get to lose my double bond. So let's look at an example. So that's a general form of hydrohalogenation. So if I take this molecule and I add HBr, what is the product? Well, this is what I get. Right? This is the product. Now I notice I add a hydrogen and I also added a bromine. So that is the HBr. Now we need to talk about what we call Markovnikov Rule. So if we talk about Markov's rule, it says that the nucleophile ends up on the more substituted carbon. So nucleophile will end up on the more substituted carbon. Now I want you to think of substituted carbon as being a carbon that has less hydrogens. So in other words, if I have a carbon that looks like this, I have an R group, maybe I have an R prime, and I have two hydrogens, versus a carbon that has an R group, an R prime group, an R double prime group, and a hydrogen. This is actually more substituted. So I want you to think about the less hydrogen a carbon has. Just think about it in that respect. It is more substituted. Okay? And that is going to help us determine our products. So what if we do this example? Again, remember Markovnikov's rule says that the nucleophile will end up on the more substituted carbon. Okay? If we take this molecule and react it with HBr, this is the product that we get. Now, how do we get to this product? This is a product that we get if we take that molecule and add HBr. Well, let's look at the mechanism before we actually just go through some examples without the mechanism. So the first thing that happens in hydrohalogenation is that the double bond acts as a nucleophile. So it will come, take all the hydrogen, and then the bond between the hydrogen and bromine goes on the bromine in the form of lone pairs. That will give the bromine a negative charge. So as a result, I'm really adding the hydrogen. Now the hydrogen that I add is going to go to the less substituted carbon. So here I initially add one hydrogen, but now I just added a hydrogen, so therefore I lose my double bond. I have to have a positive charge on the carbon that has lost the double bond. Now, if you notice that this is the more substituted carbon, so if you look at, let's label this as carbon 1, and let's label this as carbon 2. Notice that this carbon, or if we look at it from this perspective, this carbon had one hydrogen, and this carbon had 0. Right? So we said that the carbon that has 0 hydrogens is more substituted. Therefore, we should expect, or nucleophile in this case, which would be the bromine, which is negatively charged, is going to be on carbon 0 because it's less substituted. So the second step in the reaction is that the bromine becomes negatively charged. It acts as a nucleophile and attack that central carbon. So essentially, the final product, like we mentioned above, is in fact this molecule. You would expect to see 100% of this molecule in solution. You may also get this product, but it doesn't happen. where I add my hydrogen. There's my original hydrogen, but I added the bromine. Right, so there is the HBr. This you actually see 0% off. So again, this is the Markovnikov product. Right, so this is your Markovnikov's product. Right, again, your nucleophile being on the more substituted carbon. What about this reaction? What if we take this molecule and we added HCl? What do you think the product is? Okay. Let's predict the product of this. Pause the video, predict the product, and then we're going to go through it. Right? So if we take this molecule, the product for this reaction is actually this molecule. So how do we get to this molecule? Well, let's look at the reaction mechanism again. Again, my alkene is going to act as a nucleophile, take the hydrogen, and put these electrons in the form of lone pairs on the chlorine, giving us a negative chlorine, giving us a chlorine that's negatively charged. So as a result, I'm adding hydrogens. Now look, here I have a hydrogen, and here this is a CH2, so I have two hydrogens. So again, the left carbon that has only one hydrogen, you would expect to be more substituted. Right? So therefore, if that is the case, then I'm going to form a carbocation on the more substituted carbon, because that is where we should expect, or nucleophile in this case which would be a chlorine minus, to attack. Right here we have, instead of a CH2 now, we added a hydrogen on the less substituted carbon, so there's our CH3. Now you have to, organic chemistry is cumulative. Right? So right now as we speak, we have the carbocation on a secondary carbon, and we have the carbocation on a secondary. This is a secondary carbocation we're dealing with, right? But we actually can do a 1,2 hydride shift. We actually can do 1,2 hydride shift, where this hydrogen comes down and satisfies a positive charge, and we actually get the carbocation on now a tertiary carbocation. So we get the carbocation on now what we call a tertiary carbocation. So again, remember, a tertiary is more stable than the secondary, which is more stable than a primary carbocation. So our 1,2 hydride shift is very important in this case. Right? And then the chlorine comes in as a nucleophile, attacks the carbon, and we get our suspected product that we initially spoke of. So you have to remember your 1,2 hydride shifts and your methyl shifts as well. What about this reaction? If you took this molecule and added HBr, what do you expect the product to be? The product of this reaction is this molecule. Hydrohalogenation. Let's go through the reaction mechanism. If I take this molecule and add hydrobromic acid, the first thing that's going to occur, my double bond is going to act as a nucleophile, take the hydrogen, put these in the form of lone pairs on the bromine. So the first step is adding the hydrogen. Now remember that at this portion, this carbon has 0 hydrogens, while this carbon has 1 hydrogen, right? You have to see this in organic chemistry. We just didn't write it, but there's 1 hydrogen here. Therefore, the carbon that is 0 is more substituted. So therefore, we should expect to see our nucleophile on carbon 0 and not on carbon 1. So if that is a scenario that we have, continuing, then we form our carbocation. Here's our original hydrogen, but there's a hydrogen that we just added. And the second step of the reaction, the bromine that we form that is now negatively charged is going to simply attack the carbocation, and we get our anticipated product that we spoke of initially. So this, my friends, is the reaction of what we call hydrohalogenation.